We now move to the relativistic case. Instead of starting with energy being just a non-relativistic p squared on 2m, we now have the relativistic expression E squared equal p squared plus m squared. Remember then c equal 1. So the Hamiltonian corresponding to the energy for a relativistic system can be written as h equals square root of p squared operator plus m squared. Now substituting into the expression for the amplitude, we get, as before, we insert the completeness relation in the momentum basis. We use the fact that the state P is eigenstate of the operator P, and we also recall the expression giving an expression for the amplitude without gates, bras, and operators, where we used Q equal QF minus QI. In the non-relativistic case, we obtained Gaussian integral. Here, this is not a Gaussian integral. However, we can use the stationary phase approximation to approximate what this integral is when the exponential term oscillates very rapidly with a variable p. You probably have seen an application of the stationary phase approximation earlier. However, let me just remind briefly how it works. When the function f oscillates rapidly with the variable p, we see that the real part and the imaginary part of the exponential oscillates rapidly between -1 and 1. So summing over p gives essentially 0, except when the function f doesn't vary with p, and that's obtained for the p equal p0, corresponding to a stationary point of the function f, so when the derivative of f with respect to p is equal to 0. To apply the stationary phase approximation, we need to ensure that the exponent varies rapidly with p. This is the case in particular if we choose q to be very large. In that case, a small change of p multiplied by a large value of q will induce a large change of the exponent, and therefore a rapid oscillation of the exponential. So we consider a space-like interval where q is much greater than t. We can then apply the stationary phase approximation. Using q much greater than t, we have q squared minus t squared approximatively equal to q squared, and therefore we can cancel the q squared on both sides of the equation. The problem is that the momentum we obtain is imaginary, while the integral was over a real value of p. So in order to use the stationary phase approximation, we need to do some complex analysis first. So let's look at a basic technique in complex analysis, which is pushing the contour. Take, for instance, the integral of a function f of z from z1 to z2 over dz along the real axis. We call a contour a specific path in the complex plane which connects two points. So for instance, along the real axis we have this contour C, but we could also define other contours. Imagine that our function f has a pole in M. A pole is often obtained when the function is divided by 0. It turns out that the integral of the function f along the contour C or along the contour C' gives the same result, because I can continuously deform the contour C to get contour C' without hitting a pole. However, the integral over the contour C double dash is not the same because I will have to hit the pole M in order to continuously deform C to get C dash dash. So we often use this property to change an integral over the real axis into an integral over a specific contour which will hit, for instance, a specific point which will help me solve the integral, like for instance with a stationary phase approximation. So let's apply what we just saw to solve this integral, which is over the real axis and which we saw has stationary point in the imaginary axis. Our function doesn't have a pole, so we can push the contour in order to pass through the stationary point. Let's take IM. We can now apply the stationary phase approximation to estimate our integral. Note that this is only proportional to this expression. However, what is important is to note that this is non-zero. So even if it decays exponentially with Q, we still have a non-zero probability for a particle initially in Qi to end up in Qf with a space-like event, and that, of course, breaks causality. We will see later how quantum field theory solves this problem thanks to antiparticles.